Hello and welcome back. Gamma function for beginners. You don't need to have previous knowledge. You require, of course, A-level maths. It will help if you know further maths. It will also help, of course, if you know, even if you don't know further maths, but you know how to evaluate integrals whose limits are infinity or minus infinity and that sort, known as improper integrals. Okay, what is now, I've got here a few things to do just for practice later on. So what is the gamma function? This is the definition of a gamma function. The gamma of x, this is the capital letter Greek capital gamma of x is defined by this particular integral. So what's going on? While we have x's, t's, dt's, what's going on? Well, if you have an integrand that has t in there in the integration with respect to t, this you can think of it as a constant perhaps for the integration, and therefore it will produce something which is going to be in terms of x once you evaluate it, and therefore this is actually a function of x. So just to give you a bit of an idea what's going on a little bit, if you have the gamma of 2, for example, what is the gamma of 2? We'll see in a minute that it's actually very easy to actually write an answer for that, but if you didn't know, of course you will say, look, just looking at this particular definition, this is in fact t, 2 minus 1, so it's t e to the minus t, which is a standard integration by parts. You will evaluate that and you'll get an answer. Now, is this function defined for any x? In other words, can you put any x in there? The answer is not quite. You cannot put there x cannot be equal to 0, minus 1, minus 2, minus 3, and so on. Okay, so these values do not go in. You're not allowed. So I'll just draw the graph of gamma of x. I think it might not be necessary to actually do that at this stage. It's for beginners, our first lesson. So let's not worry about it. Okay, so let's go with the first example, and that I've got on the sheet here. I'm going to be writing some results here on the right to keep for reference, and I'm going to use the questions to actually show you, give you a bit of working knowledge perhaps for all of this. So the first question is to evaluate 3 times the gamma of 6 divided by the gamma of 4. Okay, what do we do in order to evaluate this? Do we actually do some kind of integration for, as I just explained, or is there a quick way of doing this? And the answer is there is, because there are some special results. So this is some of the properties of this particular function. Okay, I'm not proving these properties here because it's, as I said, lesson number 1 and it's not really necessary. First of all, the gamma of n plus 1, okay, is equal to n factorial if n is, of course, a natural number. I don't know how to write that, including perhaps a 0. So if n is equal to 0, 1, 2, 3, and so on. Okay, so for example, the gamma of 5 is the same as a 4 factorial. And that is basically it, okay? So that is a fact which can easily be proven from first principles, from the definition. We also have another property, which I'm going to write it here, we might use it, might not use it actually on this particular one, but we might use it in later examples. So it says this is not now just integers, it could be absolutely anything. And by the way, these definitions hold for complexes, but we're going to be looking at the real cases only. The gamma of x, okay, it has a recurrence relationship. Is actually not the gamma of x. I'm going to write as a gamma of x plus 1, probably better rather than writing x minus 1. The gamma of x plus 1 is the same, it's identical to x gamma of x. So we'll see this results now. I don't want to write any more. Let's go and do the first question, and you will see all of this kind of stuff in the questions which are to follow. Okay, one way of evaluating that, since these are integer values, so I can use this result here. That is 3 times 5 factorial, okay, divided by the gamma of 4 will be 3 factorial. And I don't want to be using a calculator for something like this. You can actually evaluate that as 3 times 120 divided by 6. And of course, this will give you the answer of 60. If there's a slightly different way which uses this particular result, which actually might also make sense. So if you look at the 3 gamma of 6 divided by the gamma of 4, this will also keep the numbers smaller. 3. Let's leave the gamma of 4 on the denominator. What is the gamma of 6? The gamma of 6 is the same as 5 gamma of 5. And I can reapply this formula now for the recurrence relationship between gamma of x plus 1 and gamma of x, and say, okay, that is 3 times 5. I know I can write 15 there, perhaps I should have done, but the gamma of 5, if I put to get a 5 here, it'll be 4 gamma 4. So that's 4. Oops, I didn't write the 4, because I do stupid things sometimes. 4 gamma of 4 divided by the gamma of 4. And in this particular case, I don't care to go any further, because of course the gamma of 4 will cancel, and all I've got up there is of course the answer of 60. And the question is done. So that's the first manipulation using gamma functions. I'm going to look at a few evaluations that play around with these formulas. No integration as such for the first few examples. Okay, and the next example that we got to do from our list, so we've done with this one, is 60 gamma of 5, 60 gamma of 5 divided by the gamma of 7. Okay, we can actually say that is of course, the gamma of 5 is of course 4 factorial, so 60 times 4 factorial divided by 6 factorial, and bang into a calculator. But because I can't be bothered now, the numbers are a little bit big, I'm going to do a similar sort of trick like I've done in the previous example. So I'm going to say, look, this is a bigger gamma, so I'm going to reduce this gamma of 7 down. So 60 gamma of 5, and the gamma of 7 is 6 times the gamma of 6, using of course this relationship here. And I can continue further, and I can say 60 lots of the gamma of 5 is equal to 6. That's that 6 there. Perhaps I should have cancelled some of that already. I'm being stupid. And the gamma of 6 is of course 5 lots of the gamma of 5. And that's finished now, because of course this will now give us 60 divided by 30, and the answer to this particular one should be 2. Okay, and I hope you followed the second one. Let's clear the board again, and we'll look now at the third example. So these are nice and easy, gives you an idea of what these things are. The next example is not so straightforward, because we got the gamma of 3 over 2. Okay. This now we need to add another result to our list in here. And the result we need to add, I have done already a proof for this particular one. Actually, no, I haven't, tell a lie. But it's based, what you need for that proof is actually the groundwork has been done. It's known as this particular integral, e to the minus x squared dx. I've done it in a previous lecture, and I think I have already uploaded it. But for here, we just want to quote a fact. The gamma of a half is very, very special. The gamma of a half is in fact the square root of pi. So you can think of it as a special result. Let's perhaps put some bullet points there. 1, 2, 3, 4. Okay, so how do we deal now? How do we evaluate the gamma of 3 over 2? We're going to use a combination of that and that. So using the recurrence relationship, we can say the gamma of 3 over 2 is the same as a half gamma of a half, and the answer to that is of course a half square root of pi. And that's as simple as that. That is example number 3. Okay, and the number 4 is, I don't even know why I put 2 of the same in there. It's quite silly. It's the gamma of 5 over 2. Okay, it's an extra step. So the gamma of 5 over 2 is, of course, using the recurrence relation, because we go halves, we can take it all the way down to the gamma of a half. So this is going to be now 3 over 2, the gamma of 3 over 2, which of course I can actually bang in there a half root pi for that, or I can just do it again. If I didn't have that bit up there, I would have said, okay, now I need to go one more step down with this. So it's a half gamma over half. And the answer to that would have been 3/4 of the square root of pi. Nice and easy. Okay, let me just rub the board and so really check some of these answers, because I do mistakes even with silly things like that. Okay, so let's check our answers as well as we're going along. All right, so the next example for this one is the gamma of -3/2. Okay, that's not so obvious because, of course, it's something to do with this recurrence relation. This is very, very important. And of course, we've got halves and this is the square root of pi. The problem, of course, is the recurrence relation now does not work, because that will be equal, if we use that, to -5/2, the gamma of -5/2. So we're actually not doing what we need to be getting in there. We're going in the opposite direction. We need to go to the gamma of 1/2. So how are we going to manipulate something like this in order to get something sensible? Okay, so that is the question. Okay, I can actually say the following. This is the question mark. I can say the gamma of -3/2 multiplied by a -3/2 at the front will give me the gamma of -1/2. I don't know if you, perhaps I should have written it back to front. Shall I write it now, or are we following that? So if I had basically the gamma of -1/2, I'll be saying I'm going down now from -1/2 to -3/2 times the gamma of 3/2. I wrote it back to front, so that is definitely a correct relationship. Okay, so I can definitely say from this particular line that the gamma of -3/2, I'm going to multiply both sides by -2/3. It's the same as that. Perhaps I should have really rearranged this relationship and worked with that. I didn't think about it. Now it's too late. Okay, doesn't matter. So at the moment, I can actually say, okay, the gamma of -3/2 is equal to -2/3. And perhaps I'm going to go on the side in here and say, look, if I have the gamma of -1/2 and times it by -1/2 at the front, I'm going to get the gamma of 1/2. Gamma of 1/2, we're going down from this recurrence, -1/2 and gamma of -1/2. So if you look at what is the gamma of -1/2 from this one here, it should be, of course, -2 times in this across to the other side, gamma of 1/2. So that would have been times -2 gamma of 1/2. Okay, and this will simplify now to +4/3 gamma of 1/2. And of course the gamma, once we go to gamma of 1/2, we're done, because of course that's the square root of pi. I've done perhaps this in a very messy way. I do apologize, I didn't actually prepare for the lecture. I should really do some preparation work. I'm very bad with lesson planning. My teaching can be sometimes very, very bad. For this one, now in retrospect, having done this particular question, probably the best way to do this is actually to take your recurrence relation, which is there, gamma of x plus 1 is the same as x gamma x. And because we want to go in the opposite direction, we can actually say, you know what, your gamma of x, which is the smaller x, is the same as the gamma of x plus 1 divided by x. So if we're starting now with minus, what was the question? Gamma of -3/2, this one here. Okay, we could be going in and using this formula instead. It would have been much nicer and much easier. I didn't think about it. I've just done it with a lot of messy stuff in here, but I hope you followed it. Okay, here's now our next example. Our next example is one more of this type of expressions that have halves. This is actually fairly straightforward. The gamma of -1/2 divided by the gamma of a half. Having a fraction makes life easier. Okay, what can we do for something like that? If we multiply top and bottom of this fraction by minus a half, okay, so that's what I'm doing as a first step. So I'm trying to create here this relationship. Okay, what will I get in there? Well, what will I get in there? That's in fact now the gamma of a half from this line here. And at the bottom, I will have minus a half times the gamma of a half. The gamma of a half, of course, will cancel. And of course, the answer to this one should be -2. Okay, so far so good. So we've done the first 6 and we got 3 more, and the following 3 have now integrals to do. All right, so let's clear the board and attempt these integrals. All right. So the first one, I think, is very, very straightforward. Is the integral from 0 to infinity x to the 7 e to the minus x dx. I guess we can do 7 integrations by part. I'm only joking, okay? We're not going to do anything of the sort. Let's look very quickly. The variables are a little bit topsy-turvy here because, of course, of how I wrote it. I wrote it there, gamma of x, and the dummy variable there is t, and here we got x. Shall I rewrite this? Let me just rewrite it. It makes no difference whether this is x, whether this is u, whether it's y, it hardly matters. So first of all, let me just write it as t to the 7 e to the minus t dt. It's exactly the same integral. Forget about the gamma function. That is exactly the same as that. It will not make any difference. Now, if we look at this particular line and see what happens in there, this, of course, is the e to the minus t, and this exponent is x minus 1, we need a 7. This is, in fact, by definition, the gamma of 8. How do I evaluate the gamma of 8? Of course, the gamma of 8, this we haven't actually used a lot today because we didn't have whole positive numbers. I think only on the first couple of examples, maybe we did, I can't remember now. If we have whole positive numbers here, okay, this is in fact the same as 7 factorial. I don't know what 7 factorial is. Is it 5040 or something like this? I have no idea. Please do check it. I'm not taking a calculator now. That is the answer to this particular integral. There's no integration to do at all for this particular question. Okay, we're going now to the next integral. So that's 2 more questions to do on less for our first beginner's lesson on the gamma. Let's have a look what I put for this. For this, I have the integral from 0 to infinity, 2x to the power of 4 e to the power of 1 minus x dx. Okay, this does not look like what we got in there. However, we can perhaps get it to look something like that by doing some kind of substitution. Okay, what is the first step perhaps with something like this? First of all, we got a constant in there, and this constant is this e. Let me just rewrite first of all, and I'm going to factorize out of this integral. I don't know what this 2 is there anyway. I mean, it's all it will make is the whatever the answer is 2 times bigger, but where I got the question, it has a 2 in there, so let's leave it as it is. And I'm going to factorize out an e. So this integral now will become x to the 4 in there, and I have e to the minus x dx. I hope you followed this particular manipulation. All I've done is the e to the 1 minus x is e to the 1 times e to the minus x, and I just factorize the e to the 1, or just simply e on the outside. Okay, so what I've got so far is this particular quantity. All right, it's the 2e x to the 4 e to the minus x. Again, we should start getting a little bit better, and I don't really want to change this. Or shall I, for just one more example? If you look at this, the variables again are the wrong way. I mean, we're having the x instead of t's. Let me just write so everybody can see. After all, it's lesson number 1. Forget about that. Just looking at this particular line, if I just change x's for t's, it's exactly the same integral. So that's going to be t to the 4 e to the minus t dt. Limits, of course, not to infinity. Okay, so this is now, if we look at it carefully and compare with the standard definition of the gamma function, this is in fact the gamma of 5. Okay, if it's 5 minus 1 to give you your 4, of course. So that's the gamma of 5. And the gamma of 5 is, of course, where have I written it? There you go. Is, if it's a whole number in there, it's just a factorial function. So that's in fact times 4 factorial. And the answer for factorial, I think, is 24 times 2 is 48e. And as I said in the beginning, that 2 makes absolutely no difference. If that wasn't there, all would have happened. We had 24e as our answer. And we're going to look at the very last example for today. So maybe we have to do some integration at long last, maybe, I don't know. Okay, so the last integral is the integral from 0 to infinity x cubed e to the minus 4x dx. This is not quite what we have in here. Even if we swap the t's for x's, we got this extra 4 in there, which is causing us a problem. But this is not difficult to get rid of. We just need a little substitution for that. Okay, so if we look at what we're trying to get in there, we're trying to get e to the minus just a single letter. So we're going to use a substitution. Conveniently here, I'm going to use t. T is equal to 4x to go in there. So this is going to become e to the minus t. Let's differentiate it. dt by dx is going to be equal to 4. And therefore, my dx is going to be dt divided by 4. What happens to the limits? If I put 0 for my x, my t will still be 0. So 0 will map into 0. Okay, what happens in infinity? If x is infinite, 4 times as infinite is still infinite. Okay, so the limits are actually unchanged. And maybe what I also might need to get in there is, let me rewrite this in terms of x. So I need to replace this x cubed. So the x there is going to be t over 4. So this is my substitution working. So I'll put them in a little box. Okay, and now let's transform the integral and see what happens. 0 to infinity. X cubed. X cubed is going to be t cubed. 4 cubed is 64 in there. Yeah, x cubed. E to the minus t is what I've got in there. And where's my dx? My dx is dt over 4. Let's tidy this up. We're going to get 4 times 64 is 256. So 1 over 256 outside. So t cubed e to the minus t dt. And now this is some kind of gamma. Oops, I forgot the limits there. Of course, if the limits are not there, you can have this integrand. If you, I don't know, if you have minus infinity to infinity, I'm very sorry, this is not a gamma. It has to be this very special limit, okay? So if you look at this definition, this is of course 1 over 256, and we have, this is the gamma of 4. And the gamma of 4, if it's a whole number, is a factorial. So it's going to be 3 factorial divided by 256. 3 factorial is, of course, 6. Let's write it as perhaps 3 times 2 divided by 256. And if I cancel this particular quantity, I get 3 over 128. I hope I haven't made any mistakes. Okay, that's the end of the lesson. I don't have anything else for today. We've done 9 little quick questions. I mean, what do we use the gamma function for? A lot of the manipulations that you're going to see in the lessons to follow, okay, are basically evaluations of some integrals that we cannot normally do with standard techniques. Okay, that's enough for today. and I will be signing out, and I'll see you very soon.